picture. For a moment, the quietest possible kind of light. Not the warmth of a star you can see with your eyes. Not the slow glow of a planet hanging in the dark. Something gentler than that, a whisper of radio waves, traveling through the deep silence between galaxies, carrying news from somewhere we cannot find. It moves at the speed of light, slipping through empty space for millions, sometimes billions of years. It passes through clouds of cold gas. It passes through the faint webs of dust that drift between galaxies. And then, one quiet night, on a small blue planet, it brushes against a curved metal dish in the desert, and a sleeping computer wakes up just long enough to record a single fleeting pulse. That pulse lasts less than the blink of an eye, a few thousandths of a second, shorter than the time it takes you to breathe in. And in that tiny sliver of time, the signal carries with it as much energy as our sun pours out across many long days. Then it is gone. We call these signals fast radio bursts. They are some of the strangest and most beautiful puzzles in modern astronomy. And after nearly 20 years of careful listening, we still do not know for certain what makes them. One small thing. Before we drift further out, the universe has a new wonder for you every single night here. If you'd like one waiting each evening, subscribe and let it find you. The first one we ever noticed was found by accident. A graduate student was searching through old data from a radio telescope in Australia, looking for something else entirely. Buried in the recordings from years earlier was a strange, sharp pulse that did not match anything in the local sky. It seemed to come from far beyond our galaxy, from a place no one had been watching on purpose. For a while, many researchers thought it must be a mistake, maybe a glitch in the equipment, maybe a microwave oven in the telescope's break room, maybe a stray signal from a passing satellite. Years went by before anyone was sure these flashes were real. Now we have caught hundreds of them, and the question has only grown deeper. Some come once and never come again, as if a door opened somewhere in the cosmos and closed before we could turn our heads. Others repeat, sending out new flickers from the same patch of sky. Sometimes, in slow patterns we are still trying to read. A few have been traced back to distant galaxies. A small handful seem to come from places that almost no theory predicted, and the energy carried in each one is so enormous that no one has yet written down a clean, simple answer for how it could be made. There are guesses, of course, beautiful, careful, scientific guesses. One leading idea points to magnetars, which are the burnt-out cores of dead giant stars wrapped in magnetic fields so strong that the fabric of the atom itself behaves strangely near their surface. Another idea suggests that some of the bursts come from the violent merging of two compact bodies, ancient dead stars spiraling together in the deep dark. A few researchers wonder whether several different kinds of events are blending together in our data, all of them disguised as the same kind of flash. And then there is the quietest, most patient hypothesis of all, the one most astronomers set gently aside, while still leaving the door open a crack. The possibility that at least one of these signals comes from something that is not natural at all. That last idea is not the favored one. But the universe has surprised us before. For tonight, you do not need to solve any of this. You do not need to remember the names or the numbers. You only need to picture the scale of it. A signal, born in some unknown corner of the cosmos. Perhaps before our species existed, perhaps before our solar system had even taken shape. It traveled across an ocean of darkness so wide that the word distance almost loses its meaning. It crossed the vast, empty stretches between galaxy clusters. It passed through the gentle pull of unseen matter, and it arrived on Earth in a single, unrepeatable instant while we happened to be listening. Over the next few hours, We will sit with this mystery together. We will look at where these flashes seem to come from, what they might be made of, and why their nature still slips through our fingers. There is no need to chase any conclusion. The question is bigger than the answer, and for one quiet night, that is more than enough. Let us begin with the smallest piece of the puzzle, A. Fast radio burst. In the simplest words, is a pulse of radio light that arrives from somewhere in deep space, lasts only a few thousandths of a second, and then is gone. That is the whole event. A blink, a whisper, a flash so brief that if you tried to count it, it would already be over. To picture how short a millisecond really is, think of a single human heartbeat. A calm heartbeat takes about 1 full second from one thump to the next. A millisecond is 1,000th of that. In the time it takes your heart to beat once, a fast radio burst could come and go 1,000 times over. It is shorter than the click of a camera shutter, shorter than the snap of your fingers, shorter than almost anything you can feel with your own body. And yet, inside that tiny window of time, an enormous amount of energy arrives. Some of these bursts release as much energy in a millisecond as the sun releases in several days of steady shining. The sun, remember, lights an entire solar system. It warms planets across billions of miles. To pack that much output into a single brief flicker takes a source that is small, dense, and almost beyond imagining. The light itself is not the kind we see with our eyes. It is radio light, the same broad family of waves that carries music to a car, radio, or a voice to a phone. Radio waves are simply light, with very long, slow ripples. Visible light ripples trillions of times each second. Radio light ripples far less often, with waves that can be inches or feet across. Our eyes cannot catch them, but large metal dishes on the ground can. To a radio telescope, the sky is full of soft hums and gentle hisses, and once in a while, a sudden bright pop. That pop is what we are talking about tonight. A pop from very, very far away. How far is hard to grasp. Most of these bursts seem to come from outside our own galaxy, the Milky Way. Many appear to come from galaxies hundreds of millions or even billions of light years away. A light year is the distance light travels in 1 year, moving at the fastest speed anything can move. Light is quick enough to cross our entire planet 7 times in a single second. Now let it travel for a year without stopping, then for 1 billion years. The signal that reaches a radio dish on Earth, lasting 1 tiny millisecond, may have been on its way since before the first fish swam in Earth's oceans. And during all that travel, the burst kept its shape. It crossed clouds of gas, drifted past lonely stars, slipped through the dark spaces between galaxies, and still arrived as a clean, brief flash. That alone is a small wonder. The source itself, whatever it is, must be tiny. We know this because of the timing. If the object sending the burst were as wide as our sun, the light from its near side and its far side would not arrive together. The flash would smear out across many seconds. For a pulse to stay this sharp, the source can only be a few hundred miles across at most, possibly less. A whole star's worth of energy squeezed into something no bigger than a small city. What kind of object could be that small and still that powerful? That is where the open question begins. We will sit with it across many sections tonight. Some researchers think the answer is a kind of dead star with a fierce magnetic field. Others wonder if more than one kind of object is at work, and that bursts from different sources only look alike by chance. The honest answer, the one most astronomers would give over a quiet cup of tea, is that nobody is sure yet. For now, hold these simple facts in your mind. A flash of radio light, A. Duration shorter than a heartbeat, an energy larger than days of sunshine, a source no bigger than a town, a travel time of millions or billions of years, and a question still unanswered about what makes them. These are the basic pieces, the grounding, the shape of the mystery, before we start turning it over to look at its sides. In the sections that follow, we will gently lift each piece and look at it more closely. For now, let your breathing slow. Let the numbers settle. Picture a calm, dark sky, and somewhere in it, a brief and silent flicker that no one on Earth saw with their eyes, only heard with their machines. The story of how we came to know these flashes is, in many ways, the story of patient listening. It begins not with a thunderclap of discovery, but with a quiet scrape of data from a tape archive in Australia. In the year 2007, a graduate student named Duncan Lorimer asked one of his students to look back through old recordings made by the park's radio telescope. The dish had been scanning the southern sky for years, watching for pulsars, those steady ticking remnants of dead stars. Buried in the data from a recording made in 2001 was something no one had been looking for. It was a single bright spike, a pulse of radio energy lasting only a few milliseconds, gone almost as soon as it arrived. The spike had a strange property. Its higher frequencies arrived first, and its lower frequencies trailed behind, smeared out in a gentle slope of arrival times. That slope, called the dispersion measure, suggested the signal had passed through an enormous amount of thin plasma, so much in fact that it could not have come from inside our own galaxy. This was puzzling. Almost no one believed it at first. A single flash in a single old recording could easily be a glitch, or interference from a nearby device, or a passing aircraft, or even the simple hum of the instrument itself. Astronomy is full of these false alarms. So the finding sat in a quiet corner of the field for years, debated, doubted, set aside. Part of the trouble was that no one could find another one. The park's telescope kept scanning. Other dishes joined the search. Years passed with little to show. Some researchers suggested the original signal was likely terrestrial in origin. Perhaps a microwave oven door opened too soon in a nearby kitchen, or a stray pulse from a satellite. The mystery hovered in that uncertain space between discovery and mistake. Then slowly, more flashes began to appear. A second burst was reported, then a third. Each one carried that same telltale slope, that same hint of vast distances crossed. By the early 2010s, the count had crept upward. The pattern was becoming hard to dismiss. Whatever these were, they came from somewhere very far away, and they were arriving at the Earth all the time, in every direction, if only we knew where to look and when. The naming came almost casually. Astronomers began calling them fast radio bursts, or FRBs, a plain label for something they could not yet explain. The term stuck, and as the term spread, so did the hunt. New telescopes were built with this hunt in mind. Wide field arrays designed to watch huge patches of sky at once. Computers were trained to sift through floods of incoming data in real time, looking for the brief, dispersed shape of a true burst. The challenge was enormous. A fast radio burst lasts only milliseconds. If you blink, you miss it. If your detector points the wrong way, you miss it. If your filters are tuned poorly, you mistake it for noise. By the late 2010s, the trickle had become a stream. New facilities, especially a Canadian instrument called KIME, began catching bursts almost daily. The catalogue grew from a handful to dozens, then to hundreds. then to thousands, and with that flood came a deeper realization. These bursts were not rare events. They were happening across the sky constantly, perhaps thousands of times each day, far above any single telescope's view. What no one could agree on was where they came from, or why. The hunt had revealed the existence of the phenomenon, but the origin remained wide open. One camp argued that the bursts must come from a single class of object, something compact and powerful, with the magnetar as the leading guess. Another camp suggested several different sources might be producing similar-looking signals, a kind of cosmic mimicry. A few researchers held out for stranger possibilities, but most simply gathered more data and waited. The story of how we came to know these flashes is not the story of how they were made. It is the story of how we learned they exist at all. The forces that created them remain hidden. The conditions that had to be exactly right are still being worked out. We know only this: somewhere in the deep dark, perhaps in many somewheres at once, processes we do not fully understand are releasing tremendous bursts of radio light. They have been doing so for billions of years. We only began noticing in 2007. The hunt continues. Each new burst adds another small piece to a picture that has not yet come into focus. A picture whose center is still, for now, simply a question. A fast radio burst is not made of matter in the way a stone or a planet is made of matter. It is made of light. More precisely, it is made of radio waves, which sit at the long, low end of the spectrum of light, far below the colors our eyes can see. If visible light is like the bright middle of a piano keyboard, radio waves are the deep bass notes, slow and soft and very far below human hearing. And yet, these soft notes, when they reach our telescopes, carry the imprint of a journey across almost unimaginable distance. To understand what a burst is made of, we have to think about what light itself is. Light is a ripple in the electric and magnetic fields that fill all of space. When something charged moves quickly, it stirs those fields, and the ripples spread outward at the speed of light. A fast radio burst is one of these ripples, but it carries enormous energy, packed into a tiny window of time. Whatever made it had to shake the fabric of space with extraordinary force, and only for a few thousandths of a second. The signal itself, then, is not a thing you could hold. It is a pattern of waves, but the path it takes is full of things. Between us and the source lies the wide, almost empty space inside galaxies, and between galaxies and the great voids between clusters of galaxies. None of the space is truly empty. It is filled with a thin haze of free electrons, stray atoms of hydrogen, traces of helium, and faint clouds of heavier elements scattered by ancient stars. These free electrons matter a great deal. As the burst sweeps through them, the different frequencies of the radio wave slow down by slightly different amounts. The higher notes arrive first, the lower notes arrive a little later, and the signal becomes smeared in time. Researchers call this smearing the dispersion measure, and it is a kind of fingerprint left by everything the burst passed through. Many bursts show so much dispersion that the only reasonable explanation is a long crossing of intergalactic space. So, while the flash itself is made of light, it carries within it the chemistry of the universe it traveled through. The hydrogen it brushed past was forged in the first minutes after the Big Bang. The helium too, the trace heavier elements, carbon, oxygen, iron, were cooked inside the cores of stars that lived and died long before our sun was born. Every burst that reaches us has been combed by these elements, slowed by them, slightly shaped by them. It is a strange and gentle thought. The iron in your blood and the iron in the rocks under your feet came from the same kind of stellar furnaces that now lie in the path between us and a distant fast radio burst. The calcium in your bones was built inside a star. The water in the rivers and oceans of Earth may have been carried here by ancient comets and dusty fragments from the early solar system, the leftover crumbs of star formation. The same chemistry that built your body is sprinkled through the space the bursts cross. What we still do not know is the chemistry of the source itself. Is the burst created near the surface of a dense, dead star, where the matter has been crushed into a state we barely understand? Some researchers suspect the answer lies in a magnetar, a kind of neutron star whose magnetic field is unimaginably strong. Others wonder whether some bursts come from the violent meeting of two such dead stars, releasing a single flare of radio light before the wreckage falls quiet forever. Both ideas point to material so dense that a sugar cube-sized piece would weigh as much as a mountain. That density is hard to picture. A neutron star is mostly neutrons packed shoulder to shoulder, with a thin crust of more ordinary atoms on the outside. The exact recipe of that crust, what minerals form, how the layers settle, whether exotic particles appear deeper down, remains an open question. The bursts may be one of the few ways we will ever probe such matter from a distance. For now, the building blocks of the fast radio burst story are these: a flash of radio light, a long path through thin clouds of ancient elements. A source most likely made of the most extreme matter in the universe. The light that reaches our dishes tonight has been touched by everything between here and there, and shaped by something at the far end that we still cannot name with confidence. When a fast radio burst leaves its source, it does not travel through empty nothing. The space between galaxies, though far thinner than any laboratory vacuum we can make, is filled with a faint mist of free particles. Electrons drift through it, protons drift through it. Magnetic fields, soft and stretched thin, weave through it like threads through old cloth. The burst must pass through all of this on its long journey, and each step leaves a fingerprint on the signal. The first force at work is something called dispersion. When a radio pulse moves through a thin sea of charged particles, the different colors of radio light slow down by slightly different amounts. Higher frequencies arrive a little sooner. Lower frequencies lag behind. By the time the burst reaches Earth, the original sharp spike has been smeared across time, like a sound that started as a clap and ended as a soft sweep. From that smearing, astronomers can read a number called the dispersion measure. It tells them roughly how much matter the pulse pushed through on its way here. This is one of the most beautiful gifts these bursts give us. A flash that lasted less than 1,000th of a second becomes a kind of cosmic ruler. The longer the smear, the more matter the signal crossed, and the farther away its source likely sits. From this alone, researchers have learned that many bursts come from far beyond our galaxy. Some have crossed billions of years of space before tapping gently on our antennas. Magnetic fields shape the signal too. As the wave passes through them, it twists. Radio light carries a property called polarization, which is the direction the wave wiggles as it travels. A magnetic field can rotate that wiggle ever so slightly with each step the wave takes. This twist is called Faraday rotation. By measuring how much the polarization has turned, scientists can guess at the strength of the magnetic fields the burst encountered. Sometimes the answer suggests a calm path through gentle fields. Sometimes the answer suggests something wild near the source itself, a place where magnetic forces are so strong they bend the very nature of empty space. Gravity plays its quiet role as well. Galaxies sit along the path of these bursts, and each one bends space-time a little. A burst passing near a massive cluster may take a slightly longer route than one that travels through a quieter region. In rare cases, the geometry can even split a single burst into multiple images, arriving at different moments, like a stone seen through ripples on water. Researchers are still searching for clear examples of this. If they find one, it would offer a new way to weigh galaxies and to test how gravity behaves over enormous distances. Then there is the matter of what happens near the source. Whatever object produces the burst is, by every honest guess, an extreme place. Strong magnetic fields press on charged particles. Heat rises into temperatures we cannot easily picture. Pressure builds inside crusts of ultra-dense matter. One leading idea suggests that twisted magnetic fields around a young, restless neutron star can snap suddenly, the way a stretched rubber band snaps, releasing a flash of energy in a moment. Another idea suggests that two compact objects, spiraling toward each other through long ages, finally meet and discharge their stored energy in a single radio cry. Both ideas involve gravity squeezing matter for millions or billions of years before the pulse is born. Neither has been confirmed beyond doubt. The forces shaping these bursts work on timescales we can barely hold in mind. The slow draw of gravity pulls gas into a dying star over millions of years. That star collapses in seconds. Its remnant cools and twists for thousands of years. Then, in a single millisecond, something releases. The patient work of deep time becomes a brief shout of light. What remains unknown is which combination of forces matters most. Is the burst the sound of a magnetic field tearing, the whisper of a colliding pair, the hiccup of a still unnamed object? Each theory points to different forces taking the lead role. Each makes different predictions about what should follow the flash and what the host environment should look like. So far, the evidence supports several pictures at once, and no single picture wins. For tonight, it is enough to know that something out there shapes these signals. Gravity pulls, magnetism twists, pressure builds and releases. The thin sea between galaxies leaves its quiet thumbprint, and we, with our patient dishes, read what the long journey wrote upon the wave, while the source itself stays hidden behind a curtain we have not yet learned to part. To feel the strangeness of these flashes, it helps to think for a moment about scale. Not the kind of scale you can hold in your hand, but the kind that quietly bends the mind when you sit with it long enough. Begin with the burst itself. A fast radio flash lasts about 1 millisecond. That is 1,000th of a single second. If you snap your fingers, the sound you hear lasts hundreds of these flashes, laid end to end. A blink of your eye, slow and soft as it feels, could hide 300 or 400 of them inside it. The signal is shorter than any motion your body can make on purpose. Now think about the energy packed into that sliver of time. In 1 millisecond, a single fast radio burst can release as much energy as our sun pours out over several days. Some of the brightest ones may release as much as the sun gives off in a month, or even a year. Picture the sun, that steady golden disk that warms whole oceans and grows every forest. Now picture all of that output, gathered up, compressed, and let loose in a single tick, shorter than a heartbeat. That is the scale of one flash. To make this feel closer to the body, try a small picture. Imagine you could shrink the sun down to the size of a basketball, resting on the floor of a quiet room. At that scale, Earth would be a tiny peppercorn sitting about 26 yards away, drifting through still air. The nearest star beyond the sun would be another basketball, but it would be roughly 4,000 miles from your room. That is the scale of even our small corner of the galaxy, and the radio flashes do not come from anywhere nearby. They come from far outside that whole arrangement. Most fast radio bursts seem to come from other galaxies entirely. Many travel for hundreds of millions of years before they arrive. Some have been traced to galaxies more than 8 billion light-years away, meaning the signal began its trip before the Earth even formed. The light that carried the flash set out across the dark when our planet did not yet exist, drifted past uncounted stars, and arrived at a small dish on a hill on a Tuesday for 1,000th of a second. Then it was gone. Try to hold those two scales together. The thing that made the burst was probably smaller than a city. Most leading ideas point to objects only tens of kilometers across, like the dense remains of dead stars. So, a flash from something the size of a small town crosses a distance so vast that light itself spends most of the age of the universe getting here. A point, smaller than a mountain range, sends out a pulse that washes across galaxies. The energy problem is what makes researchers stop and wonder to produce that much power in that little time. From something that small, you need a process more extreme than almost anything we understand. One leading idea is that the source is a magnetar, a kind of neutron star with a magnetic field trillions of times stronger than the magnet on your refrigerator. Another idea is that some bursts come from rare, violent events between two compact dead stars meeting in the deep dark. A third group of researchers wonders whether several different kinds of objects might all be producing similar flashes, and we simply cannot tell them apart yet. The question of what sends them sits right in this gap between the very small and the very far. A grain of cosmic matter, glowing for a moment, reaching us across an ocean of space and time that is almost too wide to picture. If you laid a single millisecond against the age of the universe, it would be like comparing a single drop of rain to every drop that has ever fallen on Earth. And yet, in that drop, there is enough energy to outshine a star for days. Some nights, when you listen to numbers like these, the mind does a soft thing. It stops trying to multiply, and it just rests inside the strangeness. A tiny pulse, a vast distance, a source we cannot yet name. The flashes happen somewhere in the sky thousands of times each day, most of them unseen, falling silently through our atmosphere and continuing on. They have been doing this for as long as there have been galaxies, and for most of that time, no one was here to notice. The scale alone does not answer the question. It only sharpens it. Something very small, very far, and very bright keeps sending us notes we cannot fully read. Float above one for a moment. In your mind, a magnetar is a kind of neutron star, and a neutron star is what remains after a massive sun collapses and dies. Imagine a sphere only about 12 miles across, no wider than a small city, yet holding more mass than our own sun. The surface beneath you would be smooth in a way nothing on Earth is smooth, smoother than glass, smoother than still water, a polished shell of strange matter, packed so tightly that a single sugar cube of it would weigh as much as a mountain. The color, if you could see it at all, would shimmer in a way our eyes cannot quite hold. Some researchers picture a faint blue-white glow, the leftover heat of a young dead star. Others imagine deeper hues, dim reds and dusky oranges from cooler, older surfaces. The light would not come from fire or burning. It would come from heat so deep and so trapped that the crust itself seems to radiate from within, and around the whole sphere you would sense, more than see, a tightening of the dark. The magnetic field of a magnetar is the strongest in the known universe, trillions of times stronger than the field of our own planet. The space around you would feel taut, like a stretched skin pulled across the sky. If you could look closely at the surface, you might notice something strange. The crust is not perfectly still. It bends, it shifts, it cracks. The crust of a magnetar is thought to be the most rigid material in the universe, far harder than steel or diamond, and yet the magnetic field beneath it is so powerful that it tugs at the crust from the inside. Stress builds, pressure climbs, and then in a single quiet instant, the surface gives way. A starquake, scientists call it. A sudden snapping of a layer thinner than a human hair, releasing a burst of energy that no machine on Earth could ever contain. This is the leading idea for where many of these radio flashes come from. A magnetar twists, a crust cracks, and a wave of energy rushes out along the bent magnetic field lines. The pulse rides outward at the speed of light, slipping through the galaxy, through the dust between galaxies, across 1 billion years of empty dark, and arrives at a radio dish on Earth as a whisper, lasting only a few thousandths of a second. Standing above such a surface, you would feel none of this. The flash would already be gone before your senses could register a thing. The magnetar would seem calm, almost asleep, a still and quiet world hanging in the void. Only the instruments would know what just happened. Only the long, patient ears of radio telescopes, scattered across deserts and mountaintops, would catch the trembling echo. Researchers find this picture compelling partly because, in 2020, a magnetar inside our own galaxy released a burst that looked very much like a smaller cousin of the mysterious flashes from far away. That moment felt like a door opening. For the first time, a known object inside our own neighborhood had done the kind of thing the distant flashes do. It was not proof, it was a clue, a strong one. Still, the picture is not complete. Some bursts carry far more energy than a single magnetar starquake seems able to produce. Some repeat in patterns that do not match what we would expect from a lone, twisted star. Some seem to come from places where magnetars should not easily form. So while many researchers lean towards the magnetar idea, others wonder if the truth involves more than one kind of source. Perhaps magnetars explain part of the puzzle. Perhaps something else, something we have not yet named, explains the rest. And so we are left with this strange, vivid scene. A tiny black sphere drifting in deep space, a surface so smooth and so hard it almost does not seem real. A magnetic field bending the very vacuum around it. And every now and then, on a time scale no one can predict, a hairline crack across a frozen crust, releasing in a single millisecond more energy than our sun gives off in days. Some of these flashes will reach a telescope here, on a quiet desert night, and a small line will appear on a screen, and a researcher will lean a little closer. Other flashes will pass through empty corners of the universe, unseen by anyone, ever. The magnetars go on turning, their crusts go on creaking, and the question of whether they are truly the source or only part of the answer stays open beneath us as we drift. Beneath the simple name of fast radio burst, a quiet divide has opened. Not every flash behaves the same way. Some sources send out a single pulse and then go silent, as if the sky took one short breath and held it forever. Others come back, they flicker, sometimes weeks later, sometimes within minutes, sometimes in clusters of dozens. This split between the repeaters and the one-offs is one of the deepest puzzles in the whole story, and the deeper astronomers look, the less clear the boundary becomes. The first repeating source was a quiet shock. For years, Every known burst had been a singular event, a lone whisper from somewhere far away. Then one source began sending more. Over time it produced hundreds of flashes, all coming from the same patch of sky. That changed everything. A single pulse can be many things, including a violent ending, but a source that returns again and again cannot be something that destroyed itself. Whatever it is, it survives. So the field split into two quiet camps. One idea is that there is really only one kind of source, and the so-called one-offs are simply repeaters we have not watched long enough. Maybe they pulse once a decade or once a century, and our telescopes have only listened for a short while. Under this view, given enough patience, every burst would eventually echo. The sky just keeps its rhythm slow. A competing idea says no. The two groups are truly different. The one-offs may come from cataclysms, brief and final, while the repeaters come from objects that survive. In that case, there could be at least two separate populations producing the same kind of flash for very different reasons. Some researchers find this view more comfortable because the energies and shapes of repeating bursts often look subtly different from the one-shot pulses. The differences are small, but they may be real. Inside the repeating group, things grow stranger still. Some repeaters cluster their pulses into storms, falling silent for long stretches, and then erupting in bursts of activity. A few seem to follow gentle schedules, with windows of activity that come and go on a regular cycle. The reason is unknown. Some researchers wonder if the source is orbiting a companion, and we only see it when the geometry is right. Others suggest the source itself rotates slowly, like a lighthouse that turns once every few weeks. Neither idea has been confirmed. The non-repeaters are stranger in their own way, because they leave so little behind. By the time the burst is recognized, the moment has passed. Astronomers point every telescope they can at the spot in the sky where it came from, but often the source has gone silent. Whatever produced the flash either ended in that instant, or it sleeps so deeply that nothing more can be seen. We are left holding a single millisecond of evidence and trying to read the whole life of an object from it. There is a soft possibility that sits between the two camps. Maybe some sources begin as repeaters and slowly fade, growing quieter over centuries until they appear to fall silent forever. Or maybe a few cataclysmic events also produce afterglows of flashes that go unnoticed. The line between the two groups may not be a wall, but a slow blending, with bright young sources at one end and dim ancient ones at the other. What sits beneath the surface here is the question of identity. When we say fast radio burst, are we naming one phenomenon or several wearing the same costume? The radio flash itself is just a fingerprint of energy, and many different objects might leave a similar mark. A magnetar quake, a collision in deep space, a flare from something we have not yet imagined. They could all show up as the same brief pulse, even if their causes are nothing alike. This is part of what makes the mystery so patient. To answer it, we cannot rely on one or two detections. We need thousands. Only by collecting many bursts, mapping their shapes, their colors, their hosts, and their behaviors over time, can the picture begin to sharpen. And even then, the answer may not be simple. It may be that the universe makes these flashes in many ways, and the work ahead is to learn the difference by ear, the way one learns to tell apart two birds singing in the same dark forest. For now, the repeaters keep their slow rhythms, the one-offs keep their silence. Both kinds of source continue to arrive, faint and unannounced, from places we cannot yet name. The line between them remains a soft and shifting thing, drawn lightly across the sky, waiting for steadier hands and longer patience to redraw it. For decades, the fast radio bursts we caught all came from somewhere far away, other galaxies, distant corners of the universe. Each signal arrived after a long crossing through the dark, smeared and shaped by everything it had passed through. The sources stayed hidden, too faint to study in any detail, too quick to chase. We knew the bursts existed, but we could not put a face to them. They felt like rumors from beyond the edge of our small island in space. Then, in the spring of 2020, something shifted. A burst arrived from inside our own galaxy. It was still faint by cosmic standards, but compared to the distant flashes we had been chasing, it was loud and close and clear. 2 radio telescopes caught it at the same moment, on opposite sides of the world. And when the astronomers traced the direction back, they did not find a quiet patch of sky. They found a known object, a magnetar, a spinning magnetized remnant of a dead star, sitting only about 30,000 light years away, well within the Milky Way. For the first time, a fast radio burst had a return address. This single event changed the shape of the conversation. Before that night, magnetars were one suspect among many. Some researchers had argued the case for years, pointing to their immense magnetic fields and their habit of releasing sudden flares of energy. Others were unconvinced. The leap in scale, they said, was too large. A magnetar in our own galaxy had never been seen producing a flash bright enough to look like the distant bursts. The math felt strained. The 2020 detection did not erase that worry, but it narrowed the gap. The signal from the magnetar known as SG, our 1935 plus 2154, sat just below the brightness of the weakest extragalactic bursts on record. If you moved that same flare to a galaxy millions of light years away, it would have looked exactly like the mystery flashes we had been collecting for over a decade. The bridge between near and far suddenly seemed crossable. Still, the question of cycles remains wide open. Magnetars are restless objects. Their crusts crack and shift. Their magnetic fields twist and snap. They flare. They quiet down. They flare again. Some go silent for years before stirring back to life. There is a rhythm to their behavior, but it is not a steady one. It is more like the breathing of something that sleeps deeply and wakes without warning. And this is where the puzzle deepens. If magnetars produce all fast radio bursts, then every burst should connect to some kind of magnetar activity. Some researchers think that fits. Others are not so sure. A few repeating bursts seem to come from quiet, ordinary regions of their host galaxies, places where young magnetars should be rare. Other bursts come from dense star-forming zones, exactly where you would expect young magnetars to live. The pattern is mixed. The sky offers hints in both directions. One possibility is that magnetars cause many of the bursts, but not all of them. A second class of sources may be hiding in the data, producing flashes that look similar but come from a different physical process. Another possibility is that magnetars themselves change in ways we do not yet understand as they age, producing different kinds of bursts at different stages of their long, slow cooling. The cycles of these dead stars stretch across thousands of years, far beyond what we can watch in real time. We are catching brief glimpses of a process whose full rhythm we may never live long enough to see. What we can say is that the galactic burst of 2020 gave us a single, precious moment of nearness. It told us that something inside our own neighborhood is capable, at least once, of producing the kind of signal that had seemed to belong only to distant galaxies. It told us that the universe does not always need to whisper from a billion light years away. Sometimes it speaks from down the street, and yet that one burst has not repeated in the same way. The magnetar has stirred again, sent out smaller pulses, gone quiet, stirred again. The cycle continues without a clear pattern. Each new flare offers another piece of evidence, and each piece deepens the question rather than closing it. The sources of these flashes pulse and breathe on timescales we are only beginning to measure. We watch, we wait, we listen, and the sky keeps its own slow rhythm above us, indifferent to whether we ever fully understand the music it is making. Somewhere in the quiet sky, a faint radio source keeps a kind of schedule. It is not perfect, and it is not loud, but it returns. For a stretch of days, it sends out short, bright flashes. Then it falls silent. Then, weeks later, it begins again. Of all the strange things about fast radio bursts, this slow heartbeat may be the strangest. The first clear example came from a repeating source catalogued years ago in a distant galaxy. Astronomers watching it carefully noticed something they had not expected. The bursts seemed to cluster inside a window of about 4 days. After that window, the source went quiet for roughly 12 days. Then the window opened again. The whole cycle lasted about 16 days, over and over, like a tide coming in and going back out. A second repeater later showed a much longer rhythm, with active stretches and silent stretches spread across many months. 2 known sources, 2 very different beats, and no agreed reason for either one. The pattern is real, but the cause is wide open. One idea is that the bursting object is part of a pair. Imagine a small, dense star locked in orbit with a larger companion, the 2 of them swinging around their shared center. For part of the orbit, the bursts can escape freely toward us. For another part, a thick wind from the companion gets in the way and muffles the signal. The cycle we see would be the orbital cycle of the pair, traced out in radio light. Some models match the numbers nicely. Others struggle to explain why the bursts cluster so cleanly in time. Another idea moves the rhythm inside the burst source itself. A magnetar, a dead star with a magnetic field so strong it bends the rules of ordinary matter, might wobble as it spins. This slow wobble, called precession, would tilt its beams toward us only during certain stretches. When the beam swings away, the source goes quiet, even if the bursts keep happening. The same flashes in this picture are always being made, but we only catch them when the geometry lines up. A third possibility goes slower still. Some neutron stars are thought to spin only once every few hours, or even every few days, after long lives of slowing down. If one of those ultra-slow spinners is the source, then the windowed pattern could simply be its rotation period, written across our sky in radio light. This idea is appealing because it is so simple. It is also hard to test, because such slow spinners are not easy to confirm by other means. None of these pictures is one. The repeating source with the 16-day cycle sits inside a fairly ordinary spiral galaxy, not far from a region of active star formation. The second periodic source sits in a different kind of neighborhood altogether, tucked near an old, tightly packed cluster of stars, where new magnetars should be rare. 2 periodic bursters, 2 different homes, 2 different beats. The contrast keeps the question fresh. Most repeating sources show no clean rhythm at all. They flicker on and off in ways that look closer to random. Whether that means the periodic ones are a special subclass, or whether all repeaters are periodic and we simply have not watched long enough, remains unsettled. A burster that activates once every several years would look completely silent to a survey that has only been running for a season. The neighbors of these signals matter too. A magnetar surrounded by the dense gas of a young supernova remnant will sound different in radio light than one drifting alone in the quiet outskirts of its galaxy. The surrounding material can soak up low frequencies, smear the pulse, and shift its colors. Some researchers wonder if the on and off pattern we see is partly shaped by clumps of gas and plasma drifting between us and the source, rather than by the source itself. In that view, the rhythm is partly a property of the road, not only the traveler. The honest answer is that we are watching a small number of objects over a short slice of time, with instruments that are still learning what to look for. The periodic bursters might be binaries. They might be precessing magnetars. They might be slow rotators we have never properly seen before. They might be all three in different cases, sharing only the surface appearance of a beat. For tonight, it is enough to picture them out there, somewhere in the dark, sending out their patient signals on schedules no one yet understands. Tides of radio light, washing across the universe, keeping time with clocks we have not learned to read. When a star much heavier than our sun runs out of fuel, it collapses inward in a single silent instant. What remains can be smaller than a city, yet heavier than anything you have ever held in your mind. A single sugar cube of this matter would weigh as much as a mountain. The atoms inside have been crushed so tightly that electrons and protons have squeezed together into pure neutrons, packed so closely they nearly touch. These objects are called neutron stars, and they are among the strangest things we have ever found. A teaspoon of one would weigh about 1 billion tons on Earth. Their surfaces may be smoother than glass, with mountains only a few millimeters tall, because their gravity is so fierce that nothing taller can stand. Some of them spin hundreds of times every second, faster than the blades of a kitchen blender, throwing out beams of light that sweep across the universe like the lamp of a quiet lighthouse. Among these dead stars, a rare kind stands out. We call them magnetars, and they are thought to be the most magnetic objects in the known universe. Their magnetic fields can be 1,000 trillion times stronger than the field of the Earth. If a magnetar drifted to within half the distance of the moon, its field would scramble every credit card and disturb the iron in your blood. From thousands of light years away, it can still flick instruments on satellites with a single quiet flare. This is why magnetars sit at the center of the fast radio burst mystery. They are the only known objects that seem extreme enough, by far, to release the energy a burst demands. A typical fast radio burst pours out, in a single millisecond, as much energy as the sun gives off in several days. Some of the brightest bursts release in that flicker what the sun would take many years to produce. The number is so large that when it was first calculated, many researchers simply did not believe it. In 2020, a magnetar inside our own galaxy, known by the catalog name SGR 1935 plus 2154, did something it had never been seen to do before. It produced a short, sharp radio burst that looked very much like a weaker cousin of the bursts we see from other galaxies. The signal was about 1,000 times fainter than the brightest extragalactic flashes, but it sat on the same family tree. For the first time, a fast radio burst had been traced back to a known, named object. The leading theory had found a quiet piece of evidence, yet even this discovery did not settle the question. The galactic burst was bright by local standards, but dim compared to the most powerful bursts in the distant universe. Some of those distant flashes carry hundreds or even thousands of times more energy. It is not clear whether the same kind of magnetar could ever produce them, or whether something even more extreme is needed. One possibility is that magnetars come in many flavors, with the rarest and most violent ones hidden in faraway galaxies. Another possibility is that magnetars explain only part of the picture, and that other sources, still unidentified, account for the brightest events. The hidden power inside these dead stars is not just magnetic. Their crusts may be the strongest material in the universe, billions of times stronger than steel. When that crust shifts by even a millimeter, it can release a starquake that sends ripples through the magnetic field above. Some researchers wonder if these starquakes, or sudden tangles in the field lines, are what light up the radio sky for a single millisecond. Others think the burst might come from far above the surface, where particles are flung outward and slam into older waves of light. Both pictures fit some of the data. Neither fits all of it. There is also the puzzle of how often these flares happen. A magnetar may sit silent for decades, then erupt many times in a single week. Then it may go quiet again, with no clear warning. The energy hidden inside these stars seems to leak out in bursts and pauses we do not yet understand. The clocks inside them, if there are clocks, are not clocks we have learned to read. So tonight, as you settle deeper into the dark, picture a city-sized sphere of crushed matter, spinning quickly, wrapped in a magnetic field strong enough to bend the empty space around it. Somewhere, one of them is twitching in the silence. Whether that twitch is the answer, or only part of the answer, is something the universe has not yet decided to tell us. Picture two dead stars drifting through the deep dark, far from any sun. Each one is small, no wider than a city. Each one is dense beyond easy imagining. A single spoonful of their matter would weigh as much as a mountain. They are the cooled cores of stars that died long ago, and now they fall slowly toward each other, across the empty miles. This is the quiet picture some researchers hold in mind when they think about the one-off radio flashes. The bursts that arrive once and never speak again. The ones that do not seem to repeat, no matter how patiently the dishes listen. A merger like this would be brief. Two neutron stars spiraling inward, faster and faster, until they touch in a single bright moment. Or a neutron star falling into a small black hole, swallowed in less than a blink. The whole event might last only milliseconds. And in that brief flicker, the dying system could release a torrent of energy across many forms of light, including radio waves. One idea is that the final moments of such a merger produce a sudden, sharp pulse of radio light. The magnetic fields of the two objects, twisted and tangled by their last embrace, snap and reconnect. Charged particles surge along those broken lines. A flash escapes into the dark, then silence. Forever silence, because the source itself is gone. That last detail is the quiet, beautiful part. If a fast radio burst comes from a merger, then the thing that made it no longer exists. The signal is a kind of farewell, a final word spoken by a system that has just ceased to be. By the time the wave reaches our telescopes, billions of years may have passed, and the place where it was born is now only a faint warm scar in the cosmic background. Some researchers find this idea attractive because it would naturally explain why certain bursts never repeat. You cannot hear a voice twice from a throat that no longer exists. Other researchers are more cautious. They point out that we have not yet caught a fast radio burst, clearly arriving alongside the other signals a merger should produce. Gravitational waves, for instance, or the slow afterglow of a kilonova, the gentle glow that follows when neutron stars combine and scatter heavy elements into space. The absence of those companion signals is one of the quiet details that troubles the merger picture. Mergers are loud in many ways. They ring space-time itself. They throw off gold and platinum in faint pink clouds. If a fast radio burst comes from such an event, we might expect to see the whole orchestra, not just one fading note. So far, the matches have been hard to confirm. There are softer versions of the idea too. Perhaps a single neutron star, very old and very still, collapses on its own into a black hole. Its surface gives way. Its magnetic field, no longer supported, releases its energy in one final shudder. Some researchers call this a blitzer, a word that simply means a sudden flash from a collapsing remnant. It would be quiet beforehand and silent afterward, one pulse and nothing more. Other quiet possibilities involve the slow in-spiral of a tiny object, perhaps a primordial black hole, into a neutron star. A small dark visitor passes through the dense crust, churning the magnetic field as it goes. A burst flares out. The visitor is swallowed. The star, changed forever, drifts on in a different state. These are gentle ideas, mostly because the events themselves would be rare and brief, leaving only the faintest fingerprints. None of these pictures has been confirmed. Each rests on careful math and on what we know about how dense matter behaves under enormous strain. The textures of the models are lovely to examine, full of small details about how magnetic lines twist, how surfaces fracture, how light escapes from places where it ought to be trapped. Researchers can spend years on a single such scenario and still not know if nature uses it. What we can say softly is that the universe seems to contain at least two kinds of fast radio bursts. The ones that come back, again and again, from sources that survive their own outbursts, and the ones that arrive once, like a single struck bell, and then leave the sky still. The colliding remnant picture is one quiet way to explain that second kind. Perhaps it is right for some of them, perhaps it is right for none. The little details continue to gather, slowly, in the patient notebooks of the people who listen. Long before fast radio bursts arrived in our antennas, physicists were already imagining strange leftovers from the birth of the universe. In the late 1970s and into the 1980s, a quiet idea began to take shape in theoretical papers. The early cosmos, in its first fractions of a second, may have cooled unevenly as different regions settled into their final state. Thin defects might have been left behind. These defects had a name that sounded almost poetic. They were called cosmic strings. The idea was simple to state and very hard to test. Picture water freezing on a winter pond. The ice forms in patches, and where two patches meet, you can see a faint seam. Now imagine that seam, but stretched across the entire universe. A cosmic string would be a thread of frozen-in energy, narrower than an atom, yet carrying the weight of a mountain range in every short stretch. Some of these threads might loop back on themselves. Others might run on for billions of light years. For decades, cosmic strings stayed mostly inside the chalkboards of theorists. There was no clear way to see them. They would not glow on their own. They would not orbit anything the way a planet does. The best hope was that a passing string might bend the light from a distant galaxy in a telltale way, producing a thin doubled image of the same object. Surveys looked for that signature. The signature has not been found, at least not in any confirmed case. When fast radio bursts arrived in the conversation, some theorists wondered if cosmic strings might finally have a way to announce themselves. The reasoning went like this. If a loop of cosmic strings suddenly snapped, or if two strings crossed and rearranged, the release of energy could be enormous and very fast. A snap might dump energy into the surrounding plasma in a tiny fraction of a second. That kind of release could, in principle, look like a brief pulse of radio light traveling out across the cosmos. The history of this idea is gentle and full of careful steps. Several papers in the 2010s sketched the math. They asked whether cosmic string cusps, the sharp points where a loop folds back on itself at nearly the speed of light, could produce signals matching the durations and energies observed. The answers were mixed. Some calculations suggested the bursts could match, others suggested the predicted shapes would not quite fit what telescopes were seeing. The idea lived on, as one possibility among many. Other theorists pushed back. They pointed out that magnetars, the dense leftover cores of stars with extreme magnetic fields, were already known to exist and already known to produce sudden flares. A magnetar model did not require any new physics. The cosmic string idea required a kind of object that had never been confirmed to exist anywhere in nature, by the rule that simpler explanations should be preferred when both can fit. Magnetars stayed ahead. Cosmic strings stayed in the background as a quieter alternative. The story did not end there. Some researchers noted that even if magnetars explain most fast radio bursts, they might not explain all of them. The energies span a wide range. The repeat patterns are inconsistent. If even a small fraction of bursts come from something else, the door stays open for unusual sources. Cosmic strings remain on the list of long-shot candidates. So do primordial black holes, and so do exotic dark matter clumps. None has been confirmed. None has been ruled out either. The history of cosmic strings as a theory is, in a way, a history of patience. The idea was born from pure mathematics. It survived for 40 years without a confirmed detection. It found new life when fast radio bursts gave theorists a fresh puzzle to apply it to. It may yet vanish quietly if better data favors simpler explanations. Or it may, one day, be vindicated by a single careful measurement that nobody can dismiss. There is something soothing in this slow march. Most ideas in physics do not arrive in sudden flashes of certainty. They drift in the background for decades, tested and retested, until either evidence catches up with them or the field gently moves on. Cosmic strings sit in that long, quiet middle ground. So do many of the theories now competing to explain the millisecond flashes. The work of sorting them out belongs to instruments still being built and to minds still being trained. For tonight, the strings remain hypothetical. The bursts remain unexplained. The chalkboards remain full of equations, waiting for the sky to confirm or deny them. Somewhere in that patient waiting, the mystery keeps its shape, neither solved nor abandoned, simply held open beneath the slow turning of the stars. Among all the ideas thrown at fast radio bursts over the years, one keeps surfacing and quietly fading, then surfacing again. It is the gentlest of the wild guesses and also the strangest. The thought is simply this: what if some of these flashes were not made by stars or dead stars or churning magnetic fields at all? What if a few of them were made by someone? The idea has lived on the very edge of serious discussion since the bursts were first noticed. Most researchers set it aside, and for good reason. Nature is creative. Magnetars, neutron stars, colliding remnants, and other compact objects can release astonishing amounts of energy through processes we already understand, in part. There is no need to reach for minds when matter alone will do, and yet the possibility is rarely closed completely. It is left ajar, the way a door is left open in case a guest arrives. The reasoning behind keeping that door cracked is quiet and careful. A fast radio burst is, in some ways, exactly what you would build if you wanted to send a signal across a galaxy. Radio waves travel cheaply. They pass through dust They are not blocked by the thick clouds that hide visible light. A short, sharp pulse at the right frequency could in principle cross 1 billion light years and still arrive crisp enough to notice. Some researchers have wondered, only wondered, whether a civilization wanting to be heard might choose something very much like this. The math, when people have explored it, leads in odd directions to produce a single millisecond flash, bright enough to be seen across cosmic distances. A sender would need a power source, vast beyond anything we can build. One speculative paper imagined enormous solar-powered transmitters orbiting their home star, beaming light-sail ships across the galaxy. The flashes we see in that picture would not be the message at all. They would be the leakage, the spillover, the faint edge of a beam meant for a vessel we cannot see. It is a beautiful idea, and almost certainly wrong. But almost is not the same as entirely. The counter-argument is stronger, and most researchers find it convincing. Fast radio bursts come from all directions in the sky. They appear in galaxies of every kind. They sit near star-forming regions in some cases, and near ancient quiet clusters in others. A natural origin can explain that spread without strain, because the stars and stellar corpses that might cause bursts exist almost everywhere. An artificial origin would require many civilizations scattered across the universe, all choosing similar transmitter designs, all flashing at similar moments in cosmic history. The simpler story, the one that needs the fewest assumptions, is that nature is doing this on her own. Then there is the matter of the signals themselves. When researchers have looked closely at the structure inside a burst, they have not found patterns that suggest meaning. No repeating codes, no mathematical sequences, no tidy arrangements of pulses that whisper hello. What they have found instead looks like the messy fingerprint of physics, sharp, chaotic, shaped by magnetic fields and plasma, exactly the kind of signature a violent natural process would leave behind. If anyone is trying to speak through these flashes, they have hidden their words very well. Still, the door stays open a crack, because honesty requires it. We do not yet know every kind of object the universe can build. We do not know what a truly advanced civilization, if such a thing exists, might find useful or beautiful. The history of astronomy is full of moments when something looked artificial at first and turned out to be natural. The first pulsar was nicknamed LGM-1 for Little Green Men, before its true source as a spinning neutron star was understood. That memory shapes how careful researchers are today. They check the natural explanations first, thoroughly, before allowing the stranger possibilities any room. So, the quiet possibility of other minds sits in the background of fast radio burst research, neither embraced nor entirely dismissed. Most evidence points away from it. The energies fit known objects. The distributions fit known populations. The spectra look like plasma, not like language. And yet, in the silence between bursts, the thought lingers. A flash that traveled for 1 billion years to arrive in a single millisecond is the kind of event that invites every imagination to take its turn. For tonight, you can let your mind wander toward that door without pushing it open. Picture a faraway world we will probably never find, going about its day under a different sun. Picture, just for a moment, a flicker of light leaving that place long before our planet had oceans. And then let the picture dissolve, because the universe almost certainly made the flash herself. Radio light is a quiet traveler. It is the same kind of light our eyes can see, only stretched into much longer waves. A single radio wave from a fast radio burst can be longer than a human hand. Sometimes longer than a small room. These long, gentle waves slip through the cosmos in ways that shorter light cannot. And that simple fact is part of why we hear these flashes at all. To understand the journey, picture the space between galaxies. It looks empty in pictures, but it is not truly empty. A thin haze of charged particles drifts there, spread so finely that a single grain of sand holds more matter than a vast cube of intergalactic space. This haze is called plasma. It is gas so hot and stretched that its atoms have come apart, and plasma, however thin, still touches the light that passes through it. When a radio flash crosses this haze, the longest waves slow down a little more than the shortest ones. By the time the signal reaches us, the pulse has been smeared. The high notes arrive first. The low notes arrive a heartbeat later. This smearing is faint, but it is real, and it is one of the clearest fingerprints we have of the trip itself. The connection here is gentle and beautiful. The same plasma that fills the space between galaxies also threads through the disks of galaxies themselves. It surrounds stars. It coils around magnetars. It hangs in the soft halos of dust and gas that drape every spiral arm. A radio flash, born near a dying star, may pass through the magnetic weather of its home galaxy, then the cool emptiness between galaxies, then the outer halo of our Milky Way, and finally the thin air above a radio dish on Earth. Every layer leaves a mark. Magnetism is part of the symphony too. Magnetic fields stretch across the universe in ways we are still trying to map. Some of them are weak and tangled, others curl around galaxies like invisible ribbons. When a radio wave passes through a magnetic field, the direction of its wiggle can twist a little. This twist is called Faraday rotation. By measuring it, researchers can read the magnetic history of the path the burst followed, almost like reading the rings of a tree. So a single millisecond flash carries many letters at once. One letter tells us about the plasma between galaxies. Another tells us about magnetic fields along the way. Another tells us how bright the source must have been to still arrive with enough strength to be heard. The flash itself lasts less time than a blink, yet the information packed into it spans nearly the whole journey. The connections reach further still. The sun affects the ocean by warming its surface and stirring its currents. In a quieter way, every galaxy a radio burst passes near may tug on its path, since gravity bends light no matter how long its waves. The bending is usually too small to notice, but over 1 billion light years, even small effects add up. A burst that grazes a hidden mass might arrive slightly later than its twin that took a clearer road. Some researchers wonder whether these gentle delays could one day help us map dark matter, the unseen scaffolding that holds galaxies in place. Others are not yet convinced the signals are clean enough to use this way. The question remains open. Even the Earth plays a part. Our own atmosphere can flicker the radio waves slightly as they arrive. Our planet's magnetic field touches them. The instruments that catch them sit inside that weather, listening through it. So a true measurement of a fast radio burst is a measurement of many things layered together. The source, the host galaxy, the deep space between, our galaxy's halo, our atmosphere, and the dish itself. Sorting the layers apart is part of the puzzle. This is what makes the mystery feel so connected to everything else. A flash from a distant galaxy is not an isolated event. It is a thread pulled through the whole quiet fabric of the cosmos. The plasma, the magnetism, the gravity of unseen mass, the slow drift of intergalactic gas. All of it leaves a soft signature on a pulse shorter than a heartbeat. We still do not know what kind of object lights these flashes in the first place. We know only that the universe, vast as it is, lets their faint whispers reach us across enormous distance, carrying news from places we may never visit. The signal is small. The chain of connections behind it is very, very long, and much of that chain is still being traced, gently, one burst at a time. Nothing in the universe arrives unchanged. A radio flash that began as a single sharp pulse, lasting less than the blink of an eye, slowly stretches and reshapes itself across the long road between its source and our quiet listening dishes. By the time it reaches Earth, it has become something the original burst was not. And that change, that gentle smearing of the signal, is one of the most useful clues we have for understanding where these flashes come from. The change has a name. Astronomers call it dispersion. The idea is simple enough to picture. Imagine a group of runners setting off at exactly the same moment, all carrying lanterns of different colors. They run through a thick, dusty forest. The runners with red lanterns slow down a little more than the runners with blue lanterns, because the dust tugs at them in subtly different ways. By the time they reach the far edge of the forest, they no longer arrive together. The blue lanterns appear first, the red ones trail behind. The original pulse of light has spread out into a slow sweep across colors. This is more or less what happens to a fast radio burst. The flash begins as a clean, brief pulse. Then it has to cross hundreds of millions, sometimes billions of light years. Along the way, it passes through clouds of free electrons, drifting alone in the great spaces between galaxies. These electrons gently delay the lower frequencies more than the higher frequencies. The pulse no longer arrives as a single instant. It arrives as a downward sweep, with the high notes first and the low notes following, like a soft slide down a piano keyboard. The amount of delay is called the dispersion measure. It is a number that tells us how much electron-filled space the signal had to swim through to reach us. The larger the dispersion measure, the longer the road, and by reading that number off each new flash, astronomers can estimate roughly how far the signal traveled before its quiet arrival on Earth. This is how researchers first realized that fast radio bursts were not coming from inside our galaxy. The dispersion measures were simply too large. They suggested distances far beyond the Milky Way, distances so deep that the bursts had to be crossing the open ocean between galaxies. That single change in the signal, that slow stretching, was the first hint that we were listening to something cosmological in scale. The changes do not end there. As the universe itself expands, the space the signal moves through stretches as well. The wavelengths grow longer. A burst that began at one frequency arrives at a slightly lower one, depending on how far it traveled and how much the universe expanded during its passage. Some of the most distant bursts we have caught were already reshaped by the cosmos before we even existed to detect them. They left their source while early life on Earth was still figuring out how to be more than a single cell. There is something tender about this. The flash that arrives tonight has been changing the entire way here. It is not the same shape it was when it left. It has been smeared, stretched, slowed, and reddened by everything it touched. And we read those changes like the rings on an old tree, hoping they tell us something honest about the road behind. The changes also leave open questions. Some researchers suspect that part of the dispersion happens close to the source itself, inside the dense gas of whatever galaxy or cloud the burst was born in. Others suspect that most of the smearing happens out in the long, thin haze of intergalactic space. The balance between these two contributions is still being worked out. If most of the delay is local, distance estimates could be off. If most of it is intergalactic, then fast radio bursts may become some of the most precise rulers we have ever had for measuring the unseen matter between galaxies. There is no settled answer yet. Each new burst, each new dispersion measure adds a little more information to a slowly forming picture. Year by year, the data piles up, the maps grow finer, the patterns begin to whisper, and the question of just how much of the change happens near home, near the source, and how much happens in the vast quiet between remains open. For now, it is enough to picture the signal itself, a single millisecond pulse, born somewhere unimaginably far away, traveling for ages, slowly stretching as the universe stretches around it, until it finally lands, soft and changed, in a dish on a hillside on Earth. To catch a whisper that lasts only 1,000th of a second, you need ears built on a grand scale. The dishes that listen for fast radio bursts are some of the largest and quietest machines ever made. They sit in remote valleys and high deserts, far from the soft hum of cities, tilted upward toward the dark. Some are single bowls of metal mesh, wide enough to hold a small lake. Others are sprawling fields of smaller antennas, working together as one enormous eye. The light they gather is not the kind your eyes can see. Radio waves are the longest, slowest ripples on the spectrum of light, where visible light dances in tiny waves a fraction of a hair wide. Radio waves can stretch across the length of your hand, or longer. They are gentle, low-frequency cousins of the same glow that warms your skin in sunlight, and because they are so long, they slip through dust and gas with ease, carrying news from places ordinary light cannot escape. In the cold high plains of British Columbia, a telescope shaped like 4 enormous half-pipes lies flat against the ground. It does not move. It does not turn. It simply stares straight up and lets the sky drift overhead, scanning a wide ribbon of the heavens each night. This instrument has caught more fast radio bursts than any other, partly because it watches such a generous slice of sky at once. Its surface is dull metal, painted in pale tones that catch the cold light of dawn. Far to the south, in the dry red interior of Western Australia, another array spreads across the desert. Thousands of small antennas sit like quiet sculptures in the rust-colored soil. The land around them is older than almost anywhere on Earth, weathered smooth by hundreds of millions of years. The silence there is profound. Even a phone signal from a passing plane would drown out the faint cosmic whisper they are listening for. So the radio quiet is guarded by law, by distance, and by the wide emptiness of the outback itself. In southwestern China, a single dish lies cradled inside a natural bowl in the green hills. Its surface is a mosaic of metal panels, shimmering silver under the morning sun and softening to grey as clouds drift by. The dish is so wide that a small village could fit inside its curve. Its panels can shift and flex, reshaping the bowl to focus on different patches of sky. From above, it looks like a still pool of mercury set into the forest, ringed by terraced fields. Each of these instruments gathers radio light in its own way, and each contributes a different piece of the puzzle. Some watch wide fields and catch many bursts but cannot pinpoint exactly where they come from. Others stare narrowly and slowly, capturing fine detail from one small patch of sky. To locate a burst precisely, several dishes scattered across continents must sometimes work together, combining their signals to sharpen the image. This trick lets a worldwide network behave as if it were a single telescope, as wide as the planet. The light that finally reaches these dishes is unimaginably faint. By the time a radio burst has crossed 1 billion light years of empty space, the energy that washes over an entire dish is less than the heat of a single snowflake landing on the metal. And yet, hidden inside that whisper is the signature of something colossal, a release of power that for one fleeting moment outshone whole galaxies in radio light. The contrast is part of the wonder. A storm of unthinkable violence arrives as the softest possible touch. What the dishes record is not really a sound, though scientists often translate the data into audible chirps to study them. It is a pattern of voltage, a tiny trembling in the receiver, sorted by frequency and time. From this trembling, a story can be unfolded. The colors of the burst, in the radio sense, reveal how the signal was smeared by its long passage through space. The shape of the pulse hints at the kind of object that made it. The exact arrival time, measured to fractions of a millisecond, helps narrow down its home in the sky. Still, even with all this listening, the central question stays open. Different dishes sometimes seem to favor different theories, depending on what kinds of bursts they catch best. One array sees mostly bright, isolated flashes. Another finds gentle repeaters that flicker again and again from the same point. Whether these telescopes are looking at one phenomenon or many remains uncertain. The world's quietest ears are wide open. The sky has not yet finished answering. A radio burst does not arrive as a sound. It arrives as a pattern of electric ripples in the air around a metal dish. Ripples that an antenna can feel the way a still pond feels a single dropped pebble. But once those ripples are recorded, engineers can shift them into the range of human hearing. And when they do, the burst becomes audible. Just for a moment, a soft chirp, a descending whistle, sliding from a higher pitch down toward a lower one, like a small bird calling from the far end of a long hallway. That falling note is the sound of distance itself. The high frequencies arrive first. The low frequencies trail behind, smeared by the thin gas between galaxies. When you compress that delay into something an ear can follow, you hear the whole cosmos in a single descending tone. It lasts about as long as it takes to blink. Then silence returns, and the sky listens again. Most of the time, the sky surveys are quiet. Wide, low telescopes stare upward, hour after hour, night after night, gathering a soft static hiss that fills the recording rooms below. That hiss is not nothing. It is the murmur of the galaxy itself, the warm afterglow of long dead stars, the faint thermal whisper of the dish hardware, all blended into a steady pale roar. Engineers sometimes call it the cosmic breath. You could fall asleep to it, and many of the people who work these instruments quietly do. Into that steady breath, every so often, something punches through. A new survey called KIME, built in a forested valley in Canada, looks like 4 enormous half-pipes laid side by side on the ground. It does not move. It cannot point. It simply waits as the Earth turns beneath the sky, letting the cosmos drift across its field of view. In its first full year of work, it caught hundreds of these bursts. When the team converts the strongest ones into audio, the recordings sound like soft taps, like rain hitting a tin roof. One drop at a time, each drop a galaxy away. In Australia, a different array spreads dozens of small dishes across a dry red plain. From the air, the dishes look like white flowers turned toward the same patch of sky. Their recordings, when sped up and shifted into hearing range, can sound almost musical. A short hum, a swept chirp, sometimes a faint double click, as if 2 pebbles fell into the pond, a fraction of a second apart. What those sounds actually mean is still an open question. One school of thought holds that the descending tone is purely a travel effect, sculpted entirely by the gas between galaxies. In that view, The source itself sends out a clean, flat pulse, and the long voyage stretches it into music. Another view suggests that some of the structure we hear may be carved closer to the source by magnetic fields curling around a young neutron star, or by clouds of plasma near a violent stellar remnant. If that second view is right, then the soft chirps carry information not just about distance, but about the storm that made them. Researchers are still learning which features belong to the journey and which belong to the birthplace. Few sky surveys have begun recording in real time, so that when a burst arrives, alerts can travel out to other telescopes within seconds. The hope is that another instrument, somewhere on Earth, might catch a faint afterglow before it fades. So far, most bursts vanish without a trace. The chirp lands, the alarm rings, and by the time other dishes swing into position, the source has gone silent again. Whether silence means the engine has truly switched off, or simply that it sleeps between flares, remains unresolved. There is something gentle about picturing those huge, unmoving instruments lying open to the sky, patient as fields of wheat. They do not chase, they do not hunt, they wait. The Earth turns, the stars drift overhead, and once in a while, a millisecond message arrives from a place no one has named. The dishes do not know what made the sound. The engineers do not know either. The recording is filed, the waveform is studied, the descending chirp is played back in quiet rooms, and the question deepens. Somewhere, right now, another burst is on its way. It left its source long before the survey was built, long before the valley was cleared, long before the first human ever looked up and wondered about radio waves. It has been traveling the whole time. When it arrives, it will sound like a soft falling whistle, lasting less than a heartbeat, and then it will be gone. When a fast radio burst arrives, it brings with it a quiet kind of arithmetic. Hidden inside the brief shimmer of the signal are numbers, and those numbers can point back across the sky to the place that sent it. The shape of the pulse, the way its colors arrive in slightly different moments, the angle at which it enters the dish, all of these become small pieces of a larger sum. Each burst is, in a sense, a math problem written in light, and when researchers solve it, the answer is sometimes a galaxy. The first step is finding where in the sky the burst came from. Early bursts gave only rough positions, like trying to point at one tree in a distant forest with a closed fist. Newer telescopes have learned to point with a finger, then a fingertip, then the smallest gesture imaginable. Some arrays can now place a burst inside a single galaxy, and sometimes even inside a single region of that galaxy. From there, the soft work begins. Astronomers take a long, quiet look at the host and try to read its character. A galaxy carries its own kind of biography. Its color hints at the ages of its stars. Its shape suggests how it formed. Its brightness hints at how many suns are burning inside it. By measuring these features, researchers build a portrait of the place where the burst was born. Some host galaxies turn out to be young and busy, full of bright new stars. Others are old and slow, glowing in soft golden tones, with very little new star formation at all. Both kinds have hosted fast radio bursts, and that simple difference has become one of the most interesting clues in the field. The reasoning behind this is gentle but elegant. If every burst came from young, violent objects, then every host should be a young, busy galaxy. The fact that bursts also appear in old, quiet galaxies suggests something more complex. Perhaps there are several kinds of sources. Perhaps some bursts come from neutron stars formed only recently, while others come from neutron stars that have been drifting in the dark for billions of years. The numbers do not yet force a single answer, but they narrow the possibilities, the way a slow tide reveals stones beneath shallow water. Distance enters the math as well. The smearing of the burst across radio frequencies, called the dispersion measure, gives a rough estimate of how far the signal traveled. When astronomers compare that number to the measured distance of the host galaxy, the two should roughly agree. When they do, it confirms that the burst really came from where it appears to come from. When they disagree, it hints at the signal passed through something dense along the way, or that it began its life in a region thick with hot gas. Each mismatch becomes another small question, another tug on the thread. There is a quiet beauty in how these calculations fit together. A pulse lasting 1,000th of a second can carry the imprint of 1 billion years of travel. Within it lie the slow stretch of expanding space, the soft fog of stray electrons, the gentle bending of a path through unseen halos of gas. The math used to read all of this is not complicated in spirit. It is mostly counting how long a wave takes, counting how far apart its colors arrive, counting the photons that reach the dish. The universe in this sense runs on patient bookkeeping. Still, the deeper questions hide between the digits. Why do some bursts appear in the outskirts of their galaxies, far from any obvious source of energy? Why do others sit close to the bright cores, where stars are still being born in clouds of pink and blue? One idea is that bursts in quiet outskirts come from old objects that have drifted away from their birthplaces. Another idea is that those quiet regions hide companions we had not yet noticed. Small clusters of ancient stars, perhaps, or remnants of long-dead binaries. Neither view has won, and both feel reasonable when you sit with them. Tonight, picture a soft spiral galaxy seen from far above, its arms curling outward in pale lavender and cream. Somewhere inside it, a single object once let out a brief, bright sigh in radio light. That sigh traveled for an unimaginable time before brushing the antenna of a telescope on a quiet hillside. The numbers that came with it now sit in a notebook, waiting. They are part of an answer that has not yet been written, a sum that has not yet been closed. The arithmetic is patient. So are the listeners. So, for the moment, are we. Somewhere in a distant galaxy, a radio flash flickered to life and began its long crossing of the dark. When astronomers traced it back, they found something unexpected at the other end. The burst did not come from a young, restless region of new stars. It came from the edge of an ancient globular cluster, a tight ball of stars older than almost anything in the sky. That detail mattered more than it might seem. Globular clusters are quiet, dense neighborhoods. The stars inside them are old and slow-burning. The hot, massive stars that explode and leave behind young magnetars died billions of years ago. So finding a fast radio burst inside such a place created a small, strange tension in the leading theory. If magnetars are the main source of these flashes, and if magnetars only live for a few thousand years after their birth, what was one doing in a graveyard of ancient stars? This is the fragile balance the section sits with tonight. The story of these bursts depends on conditions that must line up in just the right way. A neutron star with the right strength of magnetic field, a crust that can shift and crack, a surrounding region quiet enough for the signal to escape. Change any one of these by a small amount, and the burst may never form, or it may form and never reach us. One idea is that the magnetar near the ancient cluster was made in an unusual way. Instead of being born from a single dying star, it may have formed from a slow collision two old white dwarfs. The cooled cores of long-dead stars may have spiraled together over a vast stretch of time. When they finally merged, the combined mass could have collapsed into a fresh neutron star with a strong magnetic field. In that case, Magnetars could be born twice, once from young, exploding stars, and once from the quiet mergers of old, faded ones. Another possibility is that the source is not a magnetar at all. Some researchers wonder if certain bursts come from compact binary systems, where two dead stars orbit each other in tight, vast circles. The crowded heart of a globular cluster is one of the few places in the universe where such close pairs form easily. Stars, their bump and trade partners over billions of years, sometimes ending up locked in orbits only a few minutes long. A flash of radio light might come from the moment one of these pairs touches, or from the magnetic field of a small black hole feeding on a companion. The balance is delicate. For a burst to form, the source must be compact enough to release enormous energy in a single millisecond. For the burst to escape, the region around the source must be clear of dense plasma that would scatter and dim the signal. For us to detect it, the beam must point in our direction, and our radio dishes must be pointed in the right patch of sky at the right instant. Each of these conditions trims the list of candidates a little further. If the magnetic field of the source was slightly weaker, the burst might be too faint to cross the gulf between galaxies. If the field was slightly stronger, the energy might be released in a different form entirely. In gamma rays or X-rays, we would see, but not as radio light. The window for producing a millisecond radio flash bright enough to travel 1 billion light years and still be heard seems narrow. Yet bursts arrive often enough that thousands sweep past our planet every day. The narrow window must be opening somewhere all the time. The cluster burst added a new wrinkle to the puzzle. It suggested that whatever produces these flashes can exist in environments very different from the young, chaotic regions where most repeating sources have been traced. Perhaps the population of fast radio bursts is mixed. Perhaps several different objects, formed in different ways, all happen to make the same brief sound when they fire. Perhaps the underlying physics is shared, but the path to that physics can be reached from more than one direction. The fragile balance, then, is not only about the source itself, it is also about the way we tell the story. Each new burst, found in an unexpected place, asks us to widen the picture without losing the parts that already fit. The ancient star cluster, glittering with its faint old suns, holds at least one object capable of speaking in the same brief radio voice as a young magnetar across the universe. How that voice came to live there, in such old company, remains an open question, waiting patiently in the dark. Of all the puzzles that fast radio bursts have placed before us, the one that refuses to settle quietly is the simple matter of power. A single burst, lasting only 1,000th of a second, can release as much energy as our sun pours out across several days. Some of the brighter ones may equal what the sun emits in a month, or even longer, and all of it arrives in a flash, too short to blink at, from a place so far away that the signal has been traveling for 1 billion years or more. The problem is not that we cannot imagine energetic events. The universe is full of them. Stars explode, black holes collide, magnetic fields snap and reconnect with terrible force. The problem is fitting that much energy into such a tiny window of time, and doing it again and again in some cases, from the same small patch of sky. To picture the scale, imagine the entire output of a star, gathered across days of steady shining, compressed and squeezed into a single millisecond pulse of radio light. Then imagine that pulse focused tightly enough that it can cross most of the observable cosmos and still register on a dish back on Earth. Whatever engine produces it must be small enough that light itself can cross its width in a millisecond. which means no larger than a few hundred kilometers across, a city-sized object, releasing the energy of a star. The leading idea, as we have wandered through earlier sections, is a magnetar, a neutron star wrapped in a magnetic field so strong it warps the very space around it. When the crust of such a star cracks, or when its twisted field lines tear free and reconnect, enormous bursts of energy can escape. We know magnetars can flare. We have caught one doing it inside our own galaxy. The question is whether even the most violent magnetar event can match the brightness of the most distant bursts we have seen. Some of those distant bursts seem to carry more energy than any galactic magnetar flare has ever produced. That gap is where the puzzle sharpens. Either magnetars in other galaxies behave more violently than the ones we know, or some bursts are not magnetar bursts at all. One possibility is that we are seeing several different kinds of events lumped together under one name. Another is that the magnetar model itself is incomplete, and we have not yet understood what truly powers these flashes. Then there is the matter of repetition. A handful of sources flash over and over from the same spot. Others, as far as we can tell, fire only once and then go silent. If a burst destroys its source, like a final scream from a colliding pair of neutron stars, then it cannot repeat. But if the source survives, what stops it from firing again the next day or the next year? Some researchers wonder whether the apparent one-off bursts are simply repeaters caught between sleeps, and that with enough patience every source would eventually flash twice. Others suspect there are truly two populations with two very different engines. The energy problem grows stranger still when we consider the fastest, brightest bursts. To shine that brightly across 1 billion light years, the source must be focused, like a beam from a lighthouse, rather than a flash from a bare bulb. A beam means we only catch bursts pointed our way. For every flash we see, many more must be sweeping past empty regions of sky, unseen. The true number of bursts in the universe each day may be far higher than our counts suggest. Tens of thousands, perhaps, maybe more. What kind of object, packed into the size of a small city, can stir itself into beams of such power on a regular schedule? The honest answer is that nobody yet knows. The leading models can stretch to cover most of what we observe, but they strain at the edges. The brightest bursts ask for more energy than the models can comfortably supply. The quiet pauses between repeats ask for patterns the models cannot yet predict. This is the kind of unsolved problem that researchers describe with a kind of quiet excitement. The data are real, the signals are real, the math is real. Somewhere in the gap between what we can measure and what we can explain, there is a piece of physics waiting to be understood. It might be a new behavior of matter under impossible pressures. It might be a new way that magnetic fields can release their stored strength. It might be something we have not yet imagined at all. The mystery is wide open, and for tonight, that is a gentle place to rest. Imagine for a moment that we could stand outside of time and watch the next 1,000,000 years unfold. The sky overhead would shift in small, patient ways. Stars we know now would drift to new positions. New stars would form inside the slow folds of nearby clouds. And through all that quiet change, the flashes would keep arriving, brief, bright, scattered across the radio sky, like raindrops on a wide, dark roof. 1,000,000 years is a long time for us, but a short breath for the universe. In that span, the bursts we puzzle over tonight will still be reaching Earth. Many of them began their long crossing before our species existed. Some left their source galaxies when the first simple cells were forming in warm, shallow seas. They were already on their way. They had no idea where they were going. They will keep arriving long after the questions we asked tonight have been answered, replaced, or forgotten. What might we learn from them in that time? One quiet possibility is that they become tools rather than mysteries. Each burst carries a record of everything it passed through. The thin gas between galaxies leaves a fingerprint on the signal, smearing the high notes and the low notes by slightly different amounts. By collecting many thousands of these fingerprints, future astronomers may build a kind of map of the invisible matter spread across the cosmos. The flashes may become the rulers we use to measure the empty places. There is a competing idea, just as interesting. Some researchers wonder if the bursts will turn out to be many things at once. A few may come from Magnetars, those dense and restless dead stars with magnetic fields beyond imagining. Others may come from collisions we have not yet caught in the act, and a small fraction may come from sources we have not even thought to name. If that is true, then 1,000,000 years of patient listening will not give us one answer. It will give us a small library of answers, each one belonging to a different kind of cosmic event. 1,000,000,000 years stretches further than the mind can really hold. In that time, our sun will have grown warmer and wider. The oceans we know will be long gone. The continents will have shifted into shapes no map has ever shown. The galaxy itself will have drifted closer to its neighbor, Andromeda, and the two will be beginning their slow merger. Through all of that, the bursts will still come. The universe does not pause for any of us, and in 1,000,000,000 years, the sources themselves will have changed. Magnetars do not last forever. Their fierce magnetic fields slowly fade. The stars that will give birth to tomorrow's magnetars have not yet been born. They are still gathering, atom by atom, inside the cold pockets of distant clouds. When they finally collapse and die, they will leave behind new compact remnants. New flashes will follow. The supply of these strange signals seems endless, because the universe keeps making fresh engines to produce them. It is a gentle thought, in a way. The mystery we sit with tonight is not a small or fragile thing. It is built into how the cosmos works. New magnetars will form. Old ones will quiet down. Distant galaxies will collide and scatter their stars. Each of these slow, enormous events feeds the soft rain of millisecond pulses that reaches our telescopes. Even when our questions change, the flashes will keep coming. Some researchers wonder whether, far in the future, the bursts might also teach us something about matter itself. The signals pass through gas so thin that no laboratory on Earth can copy it. They travel through magnetic fields shaped by forces we do not fully understand. By studying how the light bends, twists, and stretches along the way, we may learn how matter behaves at the very edges of what physics can describe. The flashes may quietly become a kind of distant laboratory, one we never built and could never visit. Other voices push back gently. They remind us that the messengers can only teach us so much. The signal is brief. The information it carries is limited. 1,000,000 more bursts may sharpen our picture without ever solving it completely. That is also possible. The mystery may not end. It may simply grow more detailed, more textured, more layered, like a painting we keep stepping closer to, without ever seeing the final brushstroke. For now, all of this lies ahead. The future is patient. The flashes are patient. And somewhere, right now, a new burst is on its way, leaving its source for a journey that will outlast everything we know. Step back now, as far as you can, until the whole of it spreads out beneath you like a quiet sea. There are the galaxies, scattered in their long, slow drift. There are the threads of dark matter, weaving the cosmic web that holds everything together. There are the empty voids, wide as 10,000 suns laid end to end, where almost nothing moves at all, and somewhere in that vast hush, a single millisecond pulse leaves its source and begins the long walk toward us. The pulse will travel for 1 billion years. It will pass through the outer halos of galaxies, through clouds of cool hydrogen, through the slow, patient drift of plasma between worlds. By the time it touches a dish on Earth, the star that made it may already be gone. The signal arrives like a letter from a writer who has long since fallen silent. We cannot answer, we can only listen and wonder what hand once set it loose. This is the wider story the flashes belong to. The universe began hot and bright, and then it cooled, and from that cooling came atoms, and from atoms came stars, and from stars came every heavier thing. The iron in your blood was forged in the core of a dying sun. The calcium in your bones came from a supernova that bloomed and faded long before the Earth gathered itself from dust. The oxygen you are breathing right now was made inside a star you will never see. The fast radio bursts may be part of that same long chain. If many of them come from magnetars, then they are the cries of dead stars still working through their final restless years. The crust of such a star is iron and other heavy elements. Those elements were themselves cooked inside an even older star, one that lived and died before the magnetar ever formed. So each burst, if this picture is right, is a message passed down a line of stellar deaths, reaching back almost to the beginning. We are listening to the great-grandchildren of the first generation of stars. If instead some bursts come from colliding remnants, the story is similar in shape, only stranger. Two dead stars spiral together for millions of years, slowly losing energy to the gentle waves of gravity itself. At the last instant, they touch, and a portion of their mass becomes light, and some of that light is radio. The flash we record on a quiet Tuesday morning is the closing note of a duet that began before the dinosaurs. And if some of the bursts have a source no one has guessed yet, then they belong to a chapter of the cosmic story we have not learned how to read. That possibility, more than any other, is the one worth carrying into sleep. The universe still has rooms we have not entered. There are physics we have not written down. There are objects whose names we do not yet know. The same atoms that built the magnetars built you. The same gravity that bends a colliding pair of neutron stars also keeps your body resting on the bed. The same electromagnetic force that carries the burst across 1 billion light years is the force humming in every nerve, in every quiet thought, in the soft signals passing between cells as you grow drowsy. You are made of the same things the bursts are made of. You are listening with hands and ears that were assembled from the wreckage of stars. That is the perspective worth holding now. The mystery of the flashes is not a puzzle floating apart from us. It is a question being asked by the universe to itself. Matter that was once scattered as dust and gas has gathered into a form that can wonder where the radio pulses come from. The cosmos has grown a curious mind, and that mind is yours. And tonight it is allowed to rest. The theory still waiting for proof will keep waiting. Magnetar flares, the exotic processes, near event horizons, even the long-shot ideas the careful researchers set gently aside but never quite throw away. Each one is a candidate explanation for a signal that took longer to reach us than our species has existed. None of them yet can be called the answer. And that is all right. The flashes have been arriving for billions of years. They will keep arriving long after this night ends, and the next, and the one after that. There is no hurry. The universe is patient, and tonight, so are we. The question is still open. The sky is still listening with us. The atoms that make you are still humming in time with stars you will never see. And so we come to the quiet end of our long wandering. We have followed a signal that lasts only 1,000th of a second, and we have tried to imagine what could possibly send it. We have crossed billions of light years in our minds. We have stood beside spinning neutron stars and listened to the faint crackle of their magnetic skin. We have watched dishes in the desert tilt upward, patient as flowers turning toward a hidden sun. And after all of that, we still do not know what most of these flashes truly are. That is the gentle truth of the night sky. It holds more questions than answers, and it always has. The people who first looked up from grasslands and shorelines did not know what the stars were either. They simply watched and felt small in a good way and slept beneath a ceiling of light they could not explain. You are doing the same thing now. The signals are still arriving while you rest. Somewhere above the roof, above the clouds, above the thin blue shell of our air, the soft rain of radio light is falling. Most of it passes through walls and trees and sleeping bodies without notice. A few rare pulses come from sources so distant that the light began its trip before the first fish climbed onto land. By the time it reaches us, the galaxies that made it may no longer exist in the same shape. Picture, for a moment, a single small planet turning slowly in the dark. Its oceans shine pale blue under the light of a borrowed moon. Cities glow in soft amber threads along the coasts. Forests breathe out warm mist. The planet rolls on its quiet axis, unhurried, the way it has rolled for billions of years. From far away, our world would look like a single still pearl, resting on black velvet. Around that pearl, the wider galaxy turns even more slowly. Its spiral arms drift like cream, poured into deep coffee, taking 200 million years to complete a single sweep. Inside those arms, new stars are lighting up in pink and gold. Old stars are cooling into quiet embers. Somewhere among them, a magnetar may be twitching in its sleep, building up the strain that will one day release a flash we will record and wonder about. Beyond our galaxy, billions of others drift in their own gentle motion. They do not crowd or rush. They give one another space. Between them lies the thin, warm haze of the intergalactic medium, the same haze that smears the radio bursts and turns them into the soft chord we can decode. The universe is not empty. It is simply spacious, the way a cathedral is spacious, with room for the smallest whisper to carry. You are part of this. Your body is made of atoms that were cooked inside stars and scattered when those stars died. The iron in your blood, the calcium in your bones, the oxygen in your next slow breath. All of it once belonged to suns that no longer shine. You are, in the kindest sense, a small piece of the cosmos that learned how to wonder about itself. When a fast radio burst arrives, it is the universe sending a note to one of its own. Let that thought rest lightly on you. There is nothing to solve tonight. The mystery is patient. It has waited since 2007, and longer than that in truth, since the first burst was already crossing space, long before anyone built a telescope. It will wait until morning. It will wait until next year. It will wait through the slow turning of seasons, and the slow turning of careers, and the slow turning of the sky itself. We may learn the answer in our lifetime. New arrays are listening. New ideas are forming, or we may pass the question forward the way every generation passes its open questions to the next, like a candle handed gently from one quiet room to another. Either ending is a good ending. The wandering is the gift, so let your shoulders soften. Let your jaw unclench. Let the small worries of the day drift up and away, like sparks from a low fire. The universe is vast, and you are inside it, and that is enough. The flashes will keep arriving whether we watch or not. tonight. It is all right to simply rest beneath them, held by a sky that is unfinished, and beautiful for being so. Good night, quiet listener. Good night, small turning planet. Good night, distant magnetars and patient dishes and unread signals still on their way. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.